For today's notes, you will need IC62, which should be part 4. We're going to talk more about composite area and geometric probability today, now that we've made it through standard 14 and we've learned about all of our different shapes. This box at the top of the page is an example of what you will have available to you on your assessment resource card when you take this assessment in class. So as we go through, as a reminder of previous topics, base times height is what we would use to find the area of any type of rectangle. Base times height divided by 2 would be any kind of triangular shape. AP over 2 would be those regular polygons. So any type of shape that has multiple sides that are all congruent to one another, as well as angles. And then pi r squared is for the circle. So what you'll notice is we don't have the semicircle, so you'll have to remember for yourself that you need to divide by 2 for a semicircle. And then you'll need to obviously remember what part of the shape is the B and the H and the A and the P and the R in order to use that information well. All right, so for today's practice, it's really just examples where we're going to be looking for either a requested area or a geometric probability. So some of the areas are going to be requested as shaded, some of the probabilities are related to shaded, but others, if you look down below, are going to be related to non-shaded areas or probabilities. So we'll want to make sure that we're reading carefully for what the focus of each problem is. All right. Problem number 1, if we're looking for the shaded area, those little shaded pieces don't have any of our rectangle, triangle, regular, polygon, or circle characteristics. So that means what we're going to need to do is combine some of these in some way to either add up to be those shaded areas or to subtract away and leave behind those shaded areas. So this is actually going to be a subtraction problem where that shaded area can be found by taking the total area of the circle. So imagine everything was shaded and erasing or taking away the area of that hexagon. It's a hexagon because I counted up real quick and I saw 6 sides there. So my game plan to find that shaded area, sorry, it got a little scrunched in there, is to take the circle area and subtract away the hexagon area. So as I start working, circle area is found by using pi radius squared. And they've given me the radius of the circle right here. Starts at the center and goes out to that circle boundary. So that's going to look like pi 7 squared. And I'm going to go ahead and keep that exact for now, which means squaring the 7, but not multiplying by the pi quite yet. So that gives me the first piece of information about my shaded area. 49 pi is the total area in that picture. Now we need to work on the hexagon to try to figure out what that hexagon area is going to be equal to. And that's a regular polygon. So we're going to use this apothem times perimeter divided by 2 situation. If I'm looking for the apothem and the perimeter, it would probably be a good idea if I could see them on the picture. So I'm going to go ahead and from the center, draw in that apothem that travels and makes a right angle at the midpoint of that side. And then perimeter would be the distance all the way around that hexagon. So I don't think I'm ready to find that either. I am going to take this 7 though, and I'm going to swing that radius down so that it can form a triangle with this apothem that I drew in. We know that all of these radii are congruent, so I can copy that 7 down with it. And then because I'm missing the apothem and I'm actually missing what I need for perimeter as well, I need to find this angle at the top so that we can start thinking about whether this is going to be a special right triangle problem or a trig problem. Since this has 6 sides, I can do 360 divided by 6 and then divide that in half, or just divide by 12, double the number of sides. And that tells us that this angle we're using is 30 degrees. So this is a situation where I have a special angle. Across from the 30 is going to be that L side. Across from the 90 is that 2L side. And then across from the 60 would be the L root 3 side. If 7 is equal to 2L, I can divide by 2, and that tells me that 3.5 is equal to L, and my apothem then would be 3.5 root 3. So now I'm to the point in my hexagon area formula that I know the apothem, 3.5 root 3, and I need to track down that perimeter. So if we think off to the side, the perimeter is supposed to be the number of sides, 6, times a side length. That side length, remember, is that whole distance across. So it's going to take 3.5 and 3.5 together to give me that side length. That means the side length is 7, which means perimeter will be 42. And with that, I'm ready to go ahead and calculate. I would suggest trying to keep that area exact for now. So we are going to take 3.5 in the numerator and multiply it by 42, divide that by 2, but not include the root 3 in the calculator yet. So that hexagon area is 73.5 root 3. So up here at the top, 73.5 root 3 is going to be what we subtract away to leave behind those little shaded parts of that diagram. On our calculator, we should be able to do that all at once. So we've got 49 pi minus 73.5 root 3. And that tells us our area, which we're going to go ahead and round to 2 decimal places. 26.63 would be our shaded area. We don't have any units on that problem, so it would just be square units in general. But that would be all those little pieces around the edge there that are shaded. All right, moving ahead to number 2, I'm noticing it's the exact same picture, so hopefully I'll be able to use a lot of the work that we've already done. This time it's about probability, so I'm going to get my probability fractions set up. They want the probability that a randomly chosen point in the figure lies in the shaded, so shaded is the desired successful region, and we need to then divide that by the total area in the picture. When we think about the total area, that would just be that circle area that we have from before. So 49 pi will be the total area, and that shaded area, 26.63 with a whole bunch of other decimal places, is going to be the numerator. That's the probability we're searching for. Now, the good news is I still have that 26.63 number on my calculator, so I'm going to go ahead and divide that by, now pay attention here, 49 pi. I'm going to put in parentheses, because what these calculators will do if you don't put that whole 49 pi in parentheses is they will think you want to divide by 49, but then they'll come back in and they'll actually multiply that answer by pi, because they follow order of operations very specifically. And we don't want that. We want the entire 49 pi to be in the division part of the problem, which means we need that whole 49 pi to be in parentheses. Remember, we can write probability 3 different ways. So if we're choosing the decimal approach, we would leave 4 decimal places, so 0.1730. Or if we're choosing the fraction approach, I doubt we can make this into a fraction, so we're not going to go that route this time, since we have decimals and then more pi, which is related to decimals. But we could make that a percentage, which is the way probability is actually listed on your answer documents. So that would be 17.30%. And when you check the answers on your homework, you won't see the percent symbol. You'll just see 17.30. So whether you write your answer this way or this way, that's going to be the one that shows up in that answer bank at the bottom of your pages. But both are acceptable. All right, onward we go to number 3. So let's see what's happening here. We are again going to be focused on shaded area. Those shaded areas, again, are things we don't really have a name for. So I believe this is going to be another problem where we're going to do some subtracting. It looks like to me the total area this time is actually a rectangle. So we're going to take a rectangle and subtract away circles, but not just one. There's 6 of them there. So if I knew what the area of one circle was, I would need to remove that 6 different times to leave behind these shaded areas. All right, when I'm thinking about the rectangle, my formula is base times height. And from a few days ago, we know that the base and the height need to make a right angle. So I'm noticing that I have a height available to use. That 12 can be used as the height. I'm going to label that with an H. But what I'm missing is this base. So there must be some way to figure out what that distance is using this clue over here that the height is equal to 12. And that has to do with the fact that these circles fit perfectly inside this rectangle. So if it takes me 2 circles to travel a distance of 12, what that really means is that we have a diameter in each one of these circles equal to 6. And so if we think about traveling the opposite direction through this shape, each one of these is also going to be a diameter of 6. 6 plus 6 plus 6 gives me a length this way, which is my base, of 18. So because those circles all fit nice and neat inside that rectangle, we can use the dimension of the circle to help us figure out this other horizontal dimension in the picture. Quick multiplication of 18 times 12 tells me that my rectangle area is equal to 216. Okay, continuing on, we need 6 circles. So we need 6 pi r squareds. So if we think about what the radius is of each of these circles, we already talked about how the diameter is 6. So if we were to split that in half, that would tell us the radius is actually 3. I'll be a little bit careful here with your order of operations. We are going to multiply by 6 and pi eventually maybe, but 3 squared is up first because that's an exponent. And then 6 times 3 would be 54 pi, if we want to keep that nice and exact. So that's our 6 circles taken care of. So all that's left for us to do to find that shaded area is to take 216, subtract away 54 pi. We want to do that all at once. Don't do the subtraction and then attach the pi. The pi is only part of the 54. So 46.35. 46.35. Again, we just have generic units that are being squared for our shaded area. Okay. On to number 4. I see the same picture again, and they're asking me for probability this time. So let's read for what kind of probability we're looking for. We're looking for the probability that a randomly chosen point in the figure lies in the non-shaded. So same thing, shaded section. And then we're still going to have the total that we divide by every single time. So let's personalize this a little bit. The not shaded part of this picture is those 6 circles. And then the total area in this picture is that rectangle. So good news, we already know our 6 circle number for the numerator. That's the 54 pi number from before. And we already know our total area from the rectangle, 216. So all we need to do is take that 54 pi. Since that's the numerator, you can choose to put it in parentheses or not. It'll work either way. It's only when it's in the denominator that you have to be extra careful with that. And we're going to divide that by 216 to find our probability. So probability is going to be close to 0.7854 if we round to 4 decimal places, or if we want to write it in percentage form, 78.54% for that chance. Oops, sorry, I ran off the bottom of the screen there a little bit. All right, let's flip the page and keep rolling and see what else we run into here. On to number 5, we're looking for total area of the composite figure this time. total. That means we're not just focused on the shaded parts. So when we're looking for that total area, it is made out of a rectangle in the middle, combined together, so added to two triangles, which look like they are congruent. So two triangles that are congruent to each other. So if I could find the area of the rectangle using base times height, and then the area of two triangles using base times height over 2, but then because there's a 2 here, multiplied by 2, I'll be in business. Now what is a little bit careful, or what you need to be a little bit careful of here, is that the base and height I use for the rectangle might not match the base and height I use for the triangle, even though they're the same letter. So let's start with the rectangle and see what we can figure out. It looks like we have a side of the triangle here that is making a rectangle, that's making a right angle with this side here. So those could act as our base and our height. So it looks like our base is going to be 4. And then if I'm thinking about this vertical distance, that's actually what this 12 out here is related to. So that vertical distance from top to bottom is going to be the height of that rectangle, which gives me a 48 as the area of the rectangle. And now I'm part of the way through finding that composite area. Now, if we shift our focus to the triangles, we have a little bit of a problem, because in those triangles, I do not see any evidence of a right angle. You might assume that this is a right angle, but we don't do that. We need to make sure we know for sure. Now, what I do see in these triangles is some tick marks. And so when we were working on triangles before, we said if 2 of the sides match, the best place to draw in your height is going to be to separate those 2 sides, because what happens when you do that is you also separate this side that right angle happens to intersect with. So if that whole distance was 12, we can put a 6 here and a 6 here because we know that's going to get split up evenly. So basically what's happening in these triangles is we're actually going to use this 12 as the base, and we need to track down this height. We don't have it yet, we need to find it. But we have the 12 that we can use for the base. Now this 2 and this 2 are going to end up canceling each other out since we're looking for 2 triangles. So once I find the height, this height right here, I'm going to be able to multiply those together and plug it in to finish out this area. So if we zoom into this height, I'm going to focus on this little right triangle right here. Okay, maybe I'll highlight that a little bit so that we can see it, this little green triangle. I'm noticing that I have 2 out of the 3 sides labeled. So this looks to me like a great opportunity to use that Pythagorean theorem to help me out, where 8 is the c that needs to be squared, but will then be equal to the a squared plus the b squared, being h and 6. 64 then equals h squared plus 36. We need to subtract 36 from both sides, which leaves us with 28 equal to h squared. This is the point in time where we need to square root. And because the goal is to keep these answers exact for as long as possible, go through whatever process you use, either perfect squares, factor trees, or factor tables, to simplify that using a radical. So we should end up with a height equal to 2 root 7 when you go through that process. Which means my 2 triangles that I'm looking for can be simplified together as 24 root 7. So 24 root 7 gives me the rest that I need to come up with that total area. Now, if I wanted an exact answer, that would be it. I'm going to go ahead and type that in. So 48 plus 24 root 7 is equivalent to 111.50. That's going to be 49 rounds up to be 50. So 111.50. No units again, so just square units in general for that total area. All right. Number 6, I see the same diagram, but I'm noticing probability. So let's go ahead and set up our probability fraction and see what they're asking us to focus on. We want the probability that a randomly chosen point lies in the shaded region. The shaded region is those 2 triangles. So that 2 triangle number is going to be my numerator. And then the total area is actually what I just found. So we're going to have our 2 triangles in the numerator, the 24 root 7, and we're going to have our total area in the denominator. Now, because I'm trying to keep my answers nice and exact, I still have that total area on my screen. So I'm going to take 24 root 7, that's the numerator, and get out of that square root. For some of your calculators, you might actually need to close a parentheses to close up that square root. And then we're going to divide that by this entire answer. So again, we can use that second button, and then usually it's your negative key that will pull that whole answer down and divide by it. It's going to keep our answer as exact as possible for this probability. So rounding to 4 decimal places, we're going to have 0.5695. Or if you want to write that as a percent chance, it would be 56.95% chance that something randomly selected would be in one of the 2 triangles that are shaded versus somewhere else in that figure. All right, few more to go. Number 7, we're looking for the total area again. So when I start thinking about what's happening here, I see a rectangle in the middle and then 2 half circles. But if we put 2 half circles together, that just makes 1 whole circle. So I'm going to try to track down the rectangle area using base times height and the circle area using pi r squared. Seems like I'm ready to go with my rectangle area because that 45 could be the base and then this 10 could be the height. So that would just be 45 times 10, or 450 for that portion of the problem. And then for my circle, I just need to track down the radius. So if we think about the center of the circle, extending out in both directions means that this 10 is 2 radii put together. So if we divide that in half, we're going to come up with a radius of 5, which means that circle is going to be a total area of 25 pi. If we go ahead and calculate 450 plus 25 pi, this would be the best we could do if the goal was an exact answer. But if we want a decimal answer that we can round, we can go ahead and type that addition problem in. 528.54, it looks like. So total area, rounded version, 528.54 square units. Number 8 is a completely new figure, so that's the first time these haven't gone together. So we're starting fresh. We want total area again. So let's see what we think this shape is made out of. I see a semicircle, so a half circle on top, and then a triangle on the bottom. So for that semicircle, we're going to do pi r squared over 2. And for the triangle, we're going to do base times height divided by 2. Looking at the circle, that 16 would be the diameter. So I think 8 is going to be a good number to use for the radius. So we'll have pi 8 squared over 2. 8 squared is 64, and 64 divided by 2 is 32. So 32 pi would be the exact answer for that part of the composite shape. For the triangle, I think we've got our height already sketched in here. We just don't know what it's equal to. That means we're going to be using this 16 right here as the base of the triangle. And then this mystery distance is going to be our height. So we've got 16 as the base. We just need to track down that height to finish out that area formula. I see another little opportunity here to focus on a right triangle where we know the C and the A and are solving for the B, or we know the C and the B and are solving for the A, however you want to think about it. So that means we're going to head towards Pythagorean theorem, where C squared equals A squared plus B squared. 17 squared is 289. 8 squared is 64. Go ahead and subtract, and you'll get 225 equal to h squared, which means we're ready to square root. And this time around, that's a perfect square. So we won't have to simplify a radical. We'll end up with an h that is exactly 15. So then all that's left here is to finish out this triangle calculation for area. 16 times 15 is 240. Divide that by 2, and you end up with 120. That will get added on to that semicircle area. If your goal was an exact area, that would be all you could do, because you can't add 32 pi and 120, since that one doesn't have a pi attached. If you want to approximate the area, then we can type in 32 plus 120 on our calculator and give a rounded answer of 220.53. So 220.53 square units for a rounded approximate answer. All right, we've got 2 problems left to go, and it looks like they're going to be kind of similar. We're looking for shaded area in between again. So that shaded area is going to involve taking that circle, that full area, and removing a pentagon this time instead of a hexagon. So the circle formula is still pi radius squared. That pentagon is a regular polygon, so that's going to be apothem times perimeter divided by 2. I'm noticing we don't have our radius this time for the circle, and instead we know a side length. So that's good and bad. That side length is going to be helpful when we're looking for the apothem. If that whole entire side is 9, that means that this part is 4.5. Squeeze that in there. Wrote my formula kind of close. We need to find this angle up here at the top. So remember, we've got 360 divided by twice the number of sides. So 36 degrees for this triangle, which means I'm going to need to take a little detour into tangent mode, it looks like, because I have an opposite and an adjacent. So I'm looking at tangent of 36 degrees equals 4.5 over that apothem. The variable's over in that fraction, so we're going to multiply by the denominator first. And then what ends up happening is I've got a little bit more work to do, because now that A is attached to that tangent of 36. So we'll divide both sides by the tangent of 36, and we'll get an answer for what that apothem is close to. Looks to me like 6.19, excuse me, with a bunch of other decimals. So I'm going to try to leave that on my calculator, because I'm going to need to take that number and multiply it by the perimeter and divide it by 2. So let's see if we can find perimeter real quick. This has 5 sides, and each one is equal to 9. So yes, I think we can track down our perimeter no problem. 5 times 9 would be 45. So 45 is going to fill out the rest of that formula. So we've got our apothem. We're going to multiply that by the perimeter and then divide that by 2 to finish out the area of our pentagon. So that's going to be 139 points. I might lose this, so I'm going to leave a few extra decimal places on this because I need to subtract that later from the circle. So let's call that 0.3587. I might not be able to keep that on there to do my subtraction later on. Okay, so that takes care of the pentagon part of that. Now the circle is left, and I need to be able to figure out the radius in order to do that. So I feel like I'm going to need another trig equation here to make that happen. That radius is the hypotenuse, and I already know the opposite and the reference angle of 36. So I think sine of 36 equaling the opposite over the hypotenuse is going to be the way to do that. Which means, again, the variable's over in the fraction, so we're multiplying by that denominator. And we're going to have to come back through then to get the r by itself with division. So the radius will be 4.5 divided by the sine of 36. All right, so that decimal is going to be my radius. That means I need to take pi times that radius squared. So while that radius is still sitting there on my calculator, I'm actually going to square it first to avoid rounding. So that's the radius squared. I'm going to multiply that by pi. So now that is my rounded answer for the area of the circle. And I've got my pentagon then to finish it out. I need to subtract that 139.3587 number. It was good I wrote down a few extra decimal places because that number is up top in my calculator, kind of far away by now. All right, shaded area. There it is. 44.78 square centimeters. They gave us units this time, so we don't need the U. We can use centimeters. Okay. Last one. Here we go. Geometric probability. So I'm looking for probability that a randomly chosen point in the figure lies in one of the shaded regions between the regular polygon and the circle. So just one of these versus all of them. Okay, if I was looking for the probability that it involved any of the shaded regions, I would be ready to go. My shaded area would be on top, and my circle area would be on the bottom. But I only want one of those shaded areas, so one of those little sections. So that means that this probability is actually going to be a little bit too high. So if I start here and I put my shaded area in the numerator and I put my circle area in the denominator, then I can fix that later on. To calculate this, we're going to end up with close to the right answer, but not exact since we've rounded a few of these things along the way. I do still have my shaded area answer in its complete form on my calculator. So I'm going to go ahead and take that and divide it by this pi radius squared business from before. Since I didn't do a great job, well, I guess I could use this piece right here. That circle area simplified to be 184.135. So 184.135 will be a little bit easier to type in than that whole entire denominator there. Probably should have written that in here, 184.135. Okay, so that would be the probability if they asked us the probability if they asked us to choose in any of those shaded regions, which might be honestly the way that some people interpret that question. So if so, 0.2432 or 24.32%. However, if we interpret this as being in one specific part of that shaded region, that would mean that we have too much of a chance represented here because there are 5 of these shaded regions. So if we only wanted one of those instead of all 5, we would need to take this probability and actually just divide it by 5 since they're all in equal size. So the chance of being in any one particular part of the shaded region is significantly less, 0.0486. 0.0486, or as a percent, 4.86%. We will make sure that it's very clear if this is a type of problem on the assessment, whether we want any of the shaded part or whether we want a specific one of those. So for this problem, I'll say either one of these could be your answer, but it's worth thinking and reading carefully and wondering whether you can interpret things in more than one way. All right, that's it for today. We'll see you back in class. Thanks for watching.